Hello, statistics students. Last chapter, we did one sample hypothesis test. Is mu greater than 7? Is p greater than 0.6? Something like that. In this chapter, we're doing two sample hypothesis tests where I have two populations and I want to compare either the means or the proportions of two separate populations. In the first section, we learned how to do a hypothesis test for means if we knew the two sigmas, and there was a z-test involved. Then we did a hypothesis test for means if we didn't know the sigmas, so there was a t-statistic involved. But in both of those cases, our sampling was independent. Choosing a sample from this group had no bearing on choosing what sample we got from this group over here. That changes today with dependent samples, and it goes back to something we learned last semester called matched pairs experimental design. So let's review matched pairs. Let's say I want to do a test like you're going to be doing in an upcoming project. Is the average test score for version 1 of the test different than the average test score for version 2 of the test? So I take the two smartest kids in class because academically they are matched in a way that's relevant to this test. I assign one of them to version 1, one of them to version 2. I've matched them up, the two smartest folks, assign one to one treatment, one to the other treatment. Then I take the next two people, grades 3 and 4 in the roster, assign one to version 1, one to version 2. And I go all the way down to the two lowest grades in class. I assign one to version 1, one to version 2. Now, because you've done this, the sample sizes have to be the same for each group because you took pairs and you split them. So I have n people who took version 1, and I have n people who took version 2. Now, we could have just done what we did in our previous lesson, which was independent samples. I randomly assigned some people to version 1, some people to version 2, but it's possible, not likely, but possible, all the top students go to version 1 and all the bottom students go to version 2. Yeah, we want to get rid of some of that possible variation. So by doing it this way, I have pretty much a group of people over here that's pretty much matched in ability to this group of people over here. So my two samples should be fairly, or my two samples, the group sent to version 1 and the group sent to version 2 should be evenly matched. Now what we do is we say, let's take those two highest people. So I have test score from the top person in the class and the test score from the next person in the class. I take the version 1 score minus the version 2 for that score for that group, and I get a difference. Then I take the next two students, 3 and 4, and I take the version 1 score from that person and the version 2 score from that person, from 3 and 4, and I take a difference. Then I go all the way down to 19 and 20, and the version 1 score minus the version 2 score, I've got a difference. So if I have 20 students in class, I had 10 go to version 1, 10 go to version 2, I end up with 10 differences. Now what we do is we go back to last chapter and we do a one sample t-test on these differences. Now, if the average score for version 1 is equal to the average score of version 2, then these differences should cluster around 0. So that tells us how we're going to set up our hypotheses. So in the last two sections where we were doing independent samples, we wrote mu1 equals mu2. Well, if we're doing differences, we're doing matched pairs, we want to write the null hypothesis as mu1 minus mu2 is equal to 0, because we're not really comparing group version 1 to version 2 anymore. What we're doing is we're comparing the differences between individual people taking version 1 and version 2. So the T statistic is D bar, which is you take all these differences and you do a one sample T statistic or a T test on them. So you're going to get a mean and a standard dev, a mean X bar or D bar, and a standard dev S sub D on these 10 data points. So here's your average difference minus, well, mu sub D. Well, if we think mu1 minus mu2 is 0, then the average of those differences should be 0. In our book, the current book we're using as I make this video says mu sub D, but you could still do it this way. Either way, it's still the average difference minus a hypothesized difference divided by S over root N. Well, S in this case is the standard dev of those N or 10 in this example differences divided by square root of N. So let's do the hot dog example. Let's say there are two types of hot dogs, beef and tofu. And I want to do a test and say, I think that most people think the beef tastes better. So the problem is I could do a two sample hypothesis test. I could take a random sample of people and assign them to the beef, and a random sample of people and assign them to the tofu. But let's look at what problems that creates. So let's say that I assign Riley over here to the beef group. Riley really likes hot dogs. Hot dog, hot dog, hot dog. Okay. Catherine also really likes hot dogs, but Catherine got assigned to the tofu group. Seth, who got assigned to the beef group, it doesn't matter whether, you know, what the hot dog's made of. Seth, don't want that. And same with Brian over here. So the problem is we've introduced some other variation in there. We're not measuring, in this example, we're not measuring just which hot dog tastes better. There's some variation in there that, you know, this person really likes hot dogs and this person really doesn't. So it doesn't matter which one they get. There's going to be a very big difference in the scores between these two people and between these two people. So we've introduced some variation about who likes hot dogs and who doesn't. It's not just a matter of which one tastes better. So if we were to do a matched pairs test, what I would do is I would have Riley taste both the beef and the tofu, and Riley would give the beef one a score and the tofu one a score, and we'd subtract beef minus tofu, and I'd get a difference score for Riley. So Riley really likes hot dogs, but that doesn't matter anymore. What matters is which one does Riley score higher, the beef or the tofu? And I get a difference. Seth hates hot dogs. But again, that doesn't matter. What matters is which one tastes better. So we're going to take Seth's score for beef and go beef minus tofu. And this difference is Seth's score and Catherine's and Brian's. So we've factored out the confounding variable of whether somebody likes hot dogs or not, and we're left with only a difference in taste. You know, if Riley scored the beef one higher than the tofu, this would be positive. If Riley scored the tofu one higher than the beef, this difference would be negative. And if we then do a one sample t-test on these, we compare that to 0. We take the D bar, so we'd average all of these, and of course we'd want more than 4, but we'd average these. Minus 0, because that's our hypothesized values, that they taste the same versus they don't taste the same. If they taste the same, the difference would be 0. So if we go back to our formula, we take the average difference minus 0. Then we have to calculate the standard dev of all these differences divided by the square root of the sample size. So what does this reducing variation accomplish? Well, here's our t statistic. Well, we're reducing variation, so the standard dev is going to decrease because we got rid of that variation. If we went back to the 2-sample method, where's my stuff? Here it is. You go to the 2-sample method, you see there's going to be a very wide standard dev here between you, because Riley really likes things and Seth really doesn't, and a really big standard dev over here. If you reduce the standard dev, then sigma over root n gets smaller. If sigma over root n gets smaller, then t gets bigger. If t gets bigger, then you're further and further and further away from the mean, which means your p-value is going down because we're only measuring that tail out there. And if your p-value goes down, what does that mean? If p is low, reject the hoe. So if your p-value goes down, you're more likely, and as soon as it crosses that alpha threshold, you're more likely to reject the null hypothesis and conclude that the alternate is true. So the nice thing about matched pairs and dependent hypothesis test using matched pairs is that by reducing that variation, we're able to more clearly see the differences in the tastes between the two hot dogs. And if our null is that there's no difference and the alternative is that there is a difference in the tastes, then we're more likely to detect that difference in the taste to reject the null hypothesis using a dependent sample hypothesis test. So that's all I've got for this lesson. Hope you got something out of it. Yep, I guess that's it. Have a great day.